Okay, sometimes in this game of vector spaces, we need to change our bases around when you're in V, especially when V is Rn. So your book has a theorem here, theorem 15. So we have two bases, beta, which is B1 down to Bn, and German script C, which is C1 down to Cn. So we're going to let these be bases. Let beta and C be bases for a vector space V. Then there exists a unique n by n square matrix P with underscore. This is hard to write. So this is the matrix notation. It's P taking B to C such that the x-coordinate vector corresponding to the C basis is this matrix multiplied by the x in the B coordinates. Okay. The columns of P are the C coordinate vectors of the vectors in the basis for B. Okay. So in other words, P in matrix forms, this is B1 C B2 C dot 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 Bn C. All right, so this matrix, this weird matrix P, is the change of coordinates matrix. Change of coordinates matrix from B to C. So note that multiplication by this P converts beta coordinates into C coordinates. And so in chapter 5 we do some change of basis stuff, so it's good to know how to do this, okay? And the notation is quite hard, but once you do a couple of examples you'll see. And we can go the other way with it as well, do the inverse, because this n by n matrix is invertible. Okay, so let's look at an example here. We're going to let B1, so we're working in R2, be minus 9, 1. B2 is minus 5, minus 1. C1 is 1 minus 4. And C2 is 3 minus 5. So let's see here. We're going to define, we're going to see is B1 and B2. Is this a basis for R2? Yes. And we'll let C be C1, C2. Is this also a basis for R2? Yes. Okay. So now we want to find the change of coordinates matrix. Find P of B to C. Okay. All right, so this is hard. Let's let let B1 of C equal x1 comma x2, and B2 in the C coordinates be y1, y2. Then we have, if you take the columns C1 and C2 of this matrix and multiply it by x1, x2, you get B1. And similarly, if you take C1, C2 in matrix form and multiply by y1, y2, you get B2. And so we're solving these two systems simultaneously. Okay. So this is kind of cool. You do an augmented matrix. You go, all right, C1, C2, dash, 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 B1, B2. Okay, which gives us 1 minus 4, 3 minus 5, minus 9, 1, minus 5, minus 1. Row reduce this thing. 1, 0, 0, 1. 6, 4, minus 5, minus 3. Oops. So minus 5, minus 3. Okay. So B1 in the C coordinates equals column 1 over here, 6 minus 5. And B2 in the C coordinates equals 4 minus 3. And so here's the change of basis matrix. It's equal to this guy, 6 minus 5, 4 minus 3. Okay, so let's yeah, that does it. All right, we can also go the other way with it. Which isn't too much different, but instead you have the matrix P inverse, and now you switch. It goes from B to C, and you multiply on the left by P inverse. So now you're going from C to B. There you go. And basically, at the end of the day, all you're really doing is doing this this matrix stuff here. So it's not a big deal. It gets to be a little more interesting when you start throwing P's around. So, yeah, we'll talk more about this in class when we meet.